Hello, this is Florian Wörz. I am going to talk about evidence for long-tailed hardness in stochastic local search set algorithms and how restarts are useful for such distributions. This is joint work with Jan-Hendrik Lorenz. Let's start with the motivation and aim of this talk. Stochastic local search, in short SLS, is a successful paradigm for solving the satisfiability problem of propositional logic. A recent development in this area involves the solver gap set that does not solve the original instance but a modified yet logically equivalent one. Empirically, this technique was found to be promising as it improves the performance of state-of-the-art SLS solvers. However, there is a small caveat. Currently, we only have a shallow understanding of how this modification technique affects the runtime of SLS solvers. Thus, our aim will be to model this modification process and conduct an empirical analysis of the hardness of logically equivalent formulas. Our obtained results are twofold. First, if the modification process is treated as a random process, a lognormal distribution perfectly characterizes the hardness. This implies that the hardness is long-tailed. As a second contribution, we theoretically proved that all algorithms exhibiting this long-tail property can be further improved by restarts. That means all set solvers employing this modification technique can be enhanced. For the analysis, we introduced the procedure alpha. This stands for Adjusted Logical Formula Algorithm. Alpha receives a satisfiable formula f as input. The algorithm then proceeds by adding to f a randomly generated set L of implied clauses. It finally calls an SLS solver to solve the amended clause set. Using the resolution proof system to generate resolvents of a certain width will act as a natural way to sample a set L of logically equivalent clauses for a base instance f. To obtain enough data for fitting a cumulative distribution function, CDF for short, for each base instance f, we created 5,000 modified instances, f1 up to f5000. By generating resolvent sets and randomly adding some of the resolvents, such that the number of clauses increased by 10% in expectation. One should note that we also conducted a series of experiments to rule out the influence of this precise number on our results. Then, each of these modified instances was solved 100 times, each time using a different seed. So, for instance f1, we obtained 100 flip measures. This was repeated for f2, all the way up to the last modified instance. We thus obtained these values, indicating how many flips were used to solve a modified instance with solver S when using the seed, for example. Next, we calculated the mean number of flips required to solve Fi with solver S. So, this is the row-like mean. And we care about these values here. These are the values whose hardness distribution we are going to analyze. Namely, giving such a sample, we will plot the empirical distribution function, ECDF for short. For the experiments, various instance types were used. We used theoretical as well as applied models. Our experiments investigated leading SLS solvers where the dominating component is based on Schöning's random walk procedure, SRWA. The prob-set solver family is also based on Schöning's approach. Another advancement was implemented as YALSET. The performances listed in the footnotes and similarities between the solvers were reasons for choosing them for the study. The connection to the solver gap set is of course another case in point. To give an idea of the computational effort involved, the total CPU time of all experiments amounts to 80 years. Now, let's have a look at how the hardness of an instance changes when logically equivalent clauses are added. In our paper, we demonstrated that the 3-parameter lognormal distribution provides an exceptionally accurate description of the runtime behavior. And this is true for all considered problem domains and all solvers. To illustrate this, we depict our results using two representative base instances. Instance A, depicted above, is a factorization instance that was solved by Schöning's algorithm. Instance B has a hidden solution and was solved by PropSet. We estimated the lognormal distribution's 3 parameters by applying the maximum likelihood method. Here you can see the ECDF in blue and the fitted CDF on the same graph. In both cases, we can agree that no difference between the empirical data and the fitted distribution can be seen. For the analysis, however, we should not confine ourselves to this plot type. While absolute errors can be easily observed, relative errors are more difficult to detect. In our paper, we explained why checking for deviation in the tails is especially important when studying restarts. The left tail, that is, the probabilities for very small values, can be checked visually by plotting both axes, the number of flips, and the probability, logarithmically scaled. Generally speaking, the lognormal fit accurately predicts probabilities for very short runs. Lastly, we check the probabilities for particularly hard instances. Here we use the survival function S. So if f is the CDF, then S of x defined by 1 minus f of x is the survival function. If we plot the empirical survival function and the fitted survival function, again with logarithmically scaled axes, we can easily detect errors in the right tail. Here there is a discernible deviation between A and B. For A, the lognormal fit provides an accurate description. But for B, the empirical survival function approaches 0 slower than the lognormal estimate. From the visual inspection, we can conclude that lognormal distributions seem to be well suited for describing the data. We also check this with statistical tests. We use the chi-squared test as a goodness of fit test for each base instance. If the fit is poor, then a small p-value will occur. We reject the assumption that the data follows a lognormal distribution if p is smaller than 0.05. There's a slight obstacle that complicates statistical analysis. Each of the 5,000 data points is obtained by first sampling 100 runtimes of the corresponding instance and then calculating the mean. This means that we do not work with the actual expected values, but only estimates. In other words, this implies that our data is noisy. The greater the variance in the respective instance, the greater the corresponding noise. Using the chi-squared test, some cases can be incorrectly rejected. Thus, we additionally used a bootstrap test. More details on that test can be read in our paper. Let's instead have a look at an example. The excellent representation of the runtime behavior over the entire support on instance A is also reflected in the two p-values. In contrast, for instance B, we observed that while a lognormal distribution accurately describes the main part of the distribution, the probabilities for extremely long runs are off. We see this in the respective p-values. This example shows that these two statistical tests possess the power to show an inadequate fit. Now let's have a look at all statistical results. For Schrödinger's random walk algorithm, the results look very good. The total of 5 rejected instances by the statistical tests may be attributed to so-called type 1 errors. This statement is also supported by the fact that no exceptionally low p-values that are unusual for a total of 230 samples was observed. For prop set, the number 7 out of 55 can no longer be accounted for by type 1 errors. However, one can observe that the majority of rejected instances occur for a small number of variables. If one were to consider only the instances from, let's say, 150 variables onwards, then the remaining rejected instances may be attributed to so-called type 1 errors. This raises the suspicion that there may be a limiting process involved. That is, that the hypothesis is only valid for n, the number of variables tending towards infinity. For YLZ, we notice a difference between the two statistical tests. According to the chi-square test, 2 out of the total 10 instances are rejected. However, using the bootstrap test, our hypothesis is not rejected for any instance. Therefore, we cannot rule out the possibility that log-normal distributions are the natural model, but more experiments are required to make a more precise statement. Okay, so in summary, it seems that log-normal distributions are the appropriate choice for describing runtimes for Schrödinger's random walk algorithm. For prop set, this appears plausible at least above a certain instance size. And it also seems reasonable for YLZ. These observations led us to the following conjecture. The runtime of alpha with these 3 SLS solvers follows a log-normal distribution. However, a small deviation of the probabilities would render the strong conjecture invalid from a strict mathematical point of view. Occasionally, we observed that in the right tail, the probability approaches 0 more slowly than predicted. We therefore rephrase our conjecture in a weakened form, because our observations fit a class of well-known distributions called long-tailed distributions. These are defined purely in terms of their behavior at the right tail. This is done by this expression here. So our conjecture is that the runtime follows a long-tail distribution. It should be noted that log-normal distributions have the long-tail property. That is, if the strong conjecture holds, the weak conjecture is implied. The reverse, however, is not true. In the last part of the presentation, I would like to talk about restarts in the setting of long-tail distributions. Let's have a look at the following definition. Let x be a random variable for the runtime of an SLS algorithm A on some input. For t greater than 0, the algorithm AT is obtained by restarting A after time t, if no solution was found. The random variable xt models the runtime of AT. Now, restarts are called useful if there is a t greater than 0, such that the expectation of the random variable xt is strictly smaller than the expectation of the random variable x. It was proven by the second author that if the strong conjecture holds, that is, if the runtimes are log-normally distributed, then restarts are useful. Our paper extends this result and mathematically proves that restarts are useful even if only the weak conjecture holds. That is, we show that restarts are useful for long-tailed distributions. And this is the extended result. If we have a long-tailed random variable x that has a continuous PDF, small f, and a hazard rate function r, which is defined by this expression here, then we can say under very mild assumptions that restarts are useful for x. And one should note that these assumptions here, they are not restrictive at all, since all naturally occurring long-tail distributions satisfy these conditions. Combining the above theorem with the weak conjecture, we can say that restarts are useful for alpha with all investigated SLS solvers. Let's finish the presentation with a short summary and an outlook. We have seen compelling evidence for the fact that runtime of alpha follows a long-tailed or lognormal distribution. In other work, it has been shown that the usefulness of restarts is a necessary, however not a sufficient, condition to obtain superlinear speedups by parallelization. Since we have shown that the necessary condition is presumably satisfied, this immediately raises the question of whether superlinear speedups are obtained by parallelizing alpha-type algorithms. We additionally want to pose the question whether some of the conjectures can actually be theoretically proven. It is also possible to think about further developing the technique of analyzing the runtime distribution of alpha to help better understand the behavior of so-called CDCL solvers. These kind of solvers heavily employ the technique of adding new clauses and deleting some clauses. This could be thought of as solving a new logically equivalent formula of the base instance. All that remains to say is thank you for your attention.